Hello, my lovely students. So we have 1D that I'm going to record tonight. This one is on analyzing arguments. Ooh. So this is very similar to some of the stuff we were doing in the previous section, but we're also going to be using Venn diagrams. It's kind of a weird mishmash. All right, so there's two types of logical arguments. A logical argument is a set of premises, facts, used to support a conclusion or decision. There are two main types of logical arguments that we will explore in this unit. Inductive arguments draw a general conclusion from specific premises. Not good. Example, therefore, broad generalization. Whereas deductive argument draws specific conclusions from general premise. So, broad yet truthful generalization, specific thing that falls in the purview of the generalization, conclusion. Now we're going to see there's a couple ways to actually structure that argument, but the deductive ones are what we're going to focus on. Okay, so here, cannot be proven true or false, classified based on the strength of the argument, strong or weak. So an inductive argument is not logically valid, but it can be persuasive. So the strength of the argument would be on the examples you provide. So this one, 3 premises. Robins are birds that fly. Blue jays are birds that fly. Cardinals are birds that fly. Those are all true. All birds fly. Nope. We know the ostrich doesn't fly. Several others, penguins. So even though we had all true statements, we couldn't draw that conclusion from the statements. We might be able to say something like, all the birds this person has ever seen can fly. Although that's likely not true. Most people go to the zoo at least once. Deductive arguments, though, we start from a general premise and then draw a specific conclusion. Now, there's 2 considerations here. You have to determine, is the argument valid? And if it is valid, is it then sound? So one of the requirements on sound is that it must be valid. A valid argument is one that logically follows. So the conclusion directly follows from the premises. Now, you could start with a ridiculous false premise, but if you assumed the premise was true, would the rest of the structure follow? Then it can be valid. Sound is all the premises were true and you had a valid argument, so it is also sound. So we can actually set up Venn diagrams to prove this. There it is, Venn. Okay, so got a couple of statements here to consider. Sorry, I donated platelets, so I'm a little tired. All cats are mammals. All bobcats are cats. Boko is a bobcat. Conclusion, Boko is a mammal. Okay. So I have cats, mammals, bobcats, and Boko. So when it says all cats are mammals, then that means all the things that can be called cats are included in the group of all the things that can be called mammals, but there may be more things in mammals that are not cats. So mammals is the larger set, and in this case, it's the largest set we're dealing with, so we make that the rectangle. I'm going to use black for that. And then whatever the outermost set is, we call that U for the universal set, meaning for this particular universe, this is all we consider. Because there are some arguments that hold true in a limited scope, but if you broaden or restrict your focus from that, it can break the argument just because you've like brought in extra cases that weren't considered with one universal set. Okay, so we have our mammals. all cats are mammals. So this means within our universe of mammals, there is a collection that I could get them all together and okay, nobody corrals cats, but you get the theoretical idea. And then we call all of those cats. Then we have the next premise, all bobcats are cats. So within this circle of cats, there is another group that is bobcats. And then, so those are universal broad statements that talk about groups of things. So those set up some sort of Venn diagram. Now, more complicated statements could be like, some bobcats are cats, in which case there would be overlap, but it wouldn't be full enclosure. But here we have the all statements, which I think the book sticks with for y'all. So our last one is Boko is a bobcat. So this is a specific example. So with a specific example, we're not going to draw another circle. We're going to mark where that person belongs according to the statement we were given. Boko is a bobcat, then Boko is something inside the circle. So we mark that with an X to kind of show this is where it lives. And then you can label it. So that's like a line kind of pointing from to it, as it were. So we have the X, and that's Boko. So based on where we put the X, is Boko a cat, according to our Venn diagram? Well, he's within bobcats, which is within cats. So yes, Boko is a cat. Is Boko a mammal? He's within cats, which is within mammals completely. So yes, Boko is a mammal. So this is a valid argument. It logically follows. And then sound, if Boko is an actual cat bobcat, then yes, this is sound. Which way you consider that statement is a different story. All right. Now I want to move over here and consider a slightly different scenario. So the first one I have is a specific state, a general, and then a specific statement to talk about how we're going to represent this and sound versus valid. So all parrots are birds. All right, so all parrots are within the larger set birds, and then Bob is something in that. So we have birds, and then within that, parrots. And then Bob is a parrot. So what conclusion can we draw from this? We know Bob is a parrot. We were told that. So we can also conclude Bob is a bird. So let me type that in. That is valid and sound. That all makes sense. Now I'm going to throw in a new premise. All birds are green. All right, so I have my birds, and all of those are supposed to be contained within the set of things that are green. So we could put a bigger circle, or since this is my last part of the problem, I'll go ahead and make that the rectangle. Green things. Okay, so if we assume that premise is true, the valid conclusion that follows from that is that Bob must be green. Hopefully, though, you guys are saying, but birds aren't all green. We have flamingos. They're so not green. Right. And the reason so that means the new premise I proposed is a false premise. The previous two could certainly be true. I'm sure there's a parrot named Bob out there somewhere. All parrots are birds. But my new premise, all birds are green, we know is false. So even though the conclusion is valid, it logically follows, it is not sound because I've used a false premise. So even though I did have a valid and sound conclusion I could draw from the first part, once I introduce a premise that is false, if my conclusion is based off that premise, then I can no longer claim my argument is sound. So these are both valid, but only the first is sound because all birds are green is false. All right. Yeah, I copied a PowerPoint, so it's really big. All right, now, same setup as before. The difference is that instead of using our all cats are mammals statement, we have conditionals now. So these were the ones that you can shorthand it with arrow, but it's the if-then statements that you guys were studying. And then you had the converse, the inverse, and the contrapositive. So a conditional has the form if P, then Q. If something is a P, then it must also be a Q. Or if P is true, then Q must be true. That is one of the ways to interpret a conditional statement. And on the truth table, that's what the truth table tells you. If we are told the conditional statement is true, then if we can prove P is true, Q must be true. Because if the statement was false, then I can get true for P and false for Q. But if I know the statement is true and I show P is true, then my only conclusion is Q must be true. It must follow. So a conditional statement of this form is that anything we can classify as a P can be classified as a Q. That's my weird cursive Q. So we can construct, we actually end up with the same exact diagram, but if an animal is a cat, then it is a mammal. That is the same as saying all cats are mammals. All cat animals are within the diagram for mammal. If an animal is a bobcat, then it is a cat. All bobcats are within cats. Boko is a bobcat. Put another mark. Boko is a mammal. Conclusion. So it follows the same way. It's just our premises are written slightly differently, but we still get the same conclusion. So if you have a conditional, then you can set up this subset relationship. But the catch is to remember which way you set it up. That's why I was saying if something is a P, then it is a Q. So all the things that are P's must be Q's. So the P's are the inside, the Q's are the outside. That part can feel a little weird. So affirming the hypothesis. So this is the structure of the argument I was just talking about. So if we assume our premises are true here, if you are from Buffalo, New York, then you love chicken wings. Premise, Ms. Black is from Buffalo, New York. Conclusion, Ms. Black loves chicken wings. So if we assume our premises are true, then, our universal set is all the people in the USA or New York something. Then we have, so if you are from Buffalo, then you love chicken wings. So it's all the people from Buffalo are contained in all the people that are wing lovers. And then we say Ms. Black is from Buffalo, New York. So according to our Venn diagram, that puts her within the wing lovers. So she must also love chicken wings. So this is a valid argument. It does logically flow. Yeah, let me just write that. So valid. If we assume the premises are true, then yes, the conclusion must follow. But is it sound? If you are from Buffalo, New York, then you love chicken wings. That may not be true. That is not one of those we can guarantee it to be true statements. And quite a number of conditional statements are more like opinions. So sure, you can say it, but that doesn't make it true. So because that first statement is false, then this is not a sound argument. So a lot of times it's more like thinking about, could I prove that? Not easily. All right, then we have the argument structure of affirming the conclusion. All right, so we have our same premise. If you are from Buffalo, then you love chicken wings. And then our other premise is you love chicken wings. So we have our same initial Venn diagram, but now the you love chicken wings, well, we know you're within wing lovers because you love chicken wings, but we don't know if you're inside the Buffalo circle or outside the Buffalo circle. So that's why your X goes on the line there, on the border, to show that you could be inside or outside that circle. And that circle is very much inside outside. Either you're from Buffalo or you're not. So because it's on the X, I can't guarantee for sure that you're from Buffalo, New York. You could be, but you don't have to be logically from our structure. So this is not a valid argument. I cannot guarantee my P by guaranteeing my Q. So, not writing that. So this is definitely not valid. And if it's not valid, then it's not sound. Guaranteed because of the definition of sound. So our logical structures, I can't affirm the conclusion to try to get a valid structure. And this is because if you look on the truth table, if P is false, then Q could be true or false. And my statement is still considered true because I didn't meet the initial conditions of the statement. So when I know something about the conclusion, it doesn't tell me anything about the initial statement. Just because you love chicken wings doesn't mean you have to be from Buffalo. Now, there is another argument structure called denying the hypothesis, and this one can seem a little weird at first if you're not used to the idea. So still the same premise. If you are from Buffalo, then you love chicken wings. So our same Venn diagram. But now we have a premise that you are not from Buffalo. So you are not in the purple circle any which way or form. You might be a wing lover still, or you might not. So you could be inside or outside the blue circle, but for certain you're not inside the purple circle. Then our conclusion, you do not love chicken wings. So we got if P then Q, and then you are not from Buffalo is not P, the negation of P. And then they got the conclusion you do not love chicken wings. We don't know. We put you on the line. So this is, again, not valid, so not sound. Let me go back and fill in kind of the symbolic things. So structurally, if I call you are from Buffalo P, and then you love chicken wings as Q, then that first premise is if P then Q. Then the second one is just P. So if I have if P then Q and I'm told P is true, the only line on the truth table that follows is when Q is also true. So that's like the behind the scenes what goes on here. Now we're using the Venn diagram to follow the logic instead of trying to match it on a line of the truth table. But that would be another way to think about this, is I know how conditional statements work on a truth table. So knowing that if I consider that conditional true, and then I know P is true, the only line where the conditional is true and P is true is when Q is also true. So that gives us our thus valid argument that Ms. Black should love chicken wings. So if P then Q, because we'll often conditional, you can write the arrow instead. And then we're told P, and then you put a line like this, and that's our conclusion. Some people will put the little 3 dots in a triangle for the therefore symbol. That can also symbolize the conclusion. But that's the idea on a logical argument is I have premise, premise, knowing those two, I can conclude Q. Down here, what I'm trying to say is, let's go with red. So my same, if P then Q. I get that on all of them. But this one, I got the conclusion and Q. And they tried to say, therefore, P. No. Doesn't work that way. Likewise, on denying the hypothesis, this is if P then Q, and then we got told not P. And then they tried to say, therefore, not Q. No. Conditional statements do not work that way either. Now, ironically, what this one is saying, if I start with Q, can I get P? No. And that is, they've moved in their Converse sneakers. That's the converse. The converse is not logically equivalent to the first conditional statement. Then down here, we've got negations, but we have not P and then not Q. This is the inverse, but I haven't swapped their order. The inverse is not logically equivalent to the base conditional. Ironically, the converse and the inverse are logically equivalent to each other. And you can have a statement where all 4 are true. That ends up being compressed and written as a biconditional with a double pointed arrow. So if you saw that a little on the homework as a symbol, that's where it comes from. It's when I know if P then Q is true and if Q then P is true. Then I get all 4 of my conditionals. So this last one, since we dealt with the base statement, we dealt with the converse, we dealt with the inverse, this one is the contrapositive. So our same if P then Q. And then our premise is you do not love chicken wings. That was Q, but it's not Q. Now check out our diagram. So still the same, Buffalonians inside wing lovers, but we're told that you definitely reside outside the wing lovers circle. So if you live somewhere out there, can you be from Buffalo, assuming our premises are true? No. No way, shape, or form. So not P does logically follow from this. So this one is valid. But again, because that initial statement is false, it is still not sound. But it is an excellent way to show you guys valid versus non-valid, the structure of the argument, and then we actually consider what the argument is talking about to determine if the statements, all the premises, are true. And then we can chain conditionals together. So if P then Q. So here we have, if something is a cat, then it is a mammal. So all cats are contained in mammals. If an animal is a mammal, then it has hair. All things that are mammals are contained in all things that have hair. So that's why we have animals with hair, then mammals, then cats. That's our nested setup here. So the conclusion then is something within the smallest set, the cat set. So a cat, if an animal is a cat, then it has hair, because by being in the circle, it is a mammal, and thus it is within the animals with hair. So this is what we call the transitive property. So if I label these, animal is a cat is P, mammal is Q, and then we'll say has hair is R. So the first statement is if P, then Q. The next one is if Q, then R. And then the conclusion is then, well, if P, then R. So not saying that, like, we have a cat or we have a thing with hair. We're just saying if the first two are true, the third one must logically follow from that. So this is a valid structure, and one of the classifications of being a mammal is that you have hair, hairless things being the exception, but they still do have hair. Like they usually still have eyelashes or whiskers. So it's still a mammal. All right. So this is sound, valid, and sound. Okay. So this means if I give you conditional statements, or if I give you the all statements, all A are B, or all P's are Q's, you can set up a Venn diagram to figure this out, to figure out if it's going to follow or not. So remember, if your X ends up on a borderline, you can't conclude whether it's inside or outside that line. But if your X is strictly outside it, like we had in denying the conclusion, then I can for sure say it's not in either of the inside ones. All right. So this can be weird, but this is one of the ways to structure pure logical arguments. Some people will get so hung up on the logic that they'll forget the premises also need to be true. And a lot of premises are not easy to prove. So this is the kind of thing politicians will promise. Well, if I'm elected, then I promise all sorts of things. And if they're not elected, well, they still said a true statement because they didn't get elected. So we don't know if they would have done it or not. All right, let's stop.